Hi from Tokyo, Japan, and welcome to Jeremy's IT Lab. This video is about VRF, Virtual Routing and Forwarding. VRF allows us to split one router into multiple virtual routers, each with its own routing table. It's similar to how VLANs let us split one switch into multiple virtual LANs, each with its own MAC address table. VRF is commonly used by service providers, offering MPLS Layer 3 VPNs to separate traffic from different customers. But in this video, we'll focus on VRF-lite, which lets us use VRFs on a router without MPLS to keep traffic logically separated while using shared physical hardware. I'll mostly call it VRF in this video, but just keep in mind we're talking specifically about VRF-lite. Let's get started. I mentioned VLANs in the intro. Let's quickly review how they split up a switch, and then we'll see how VRF works in a similar way with routers. Here we have one switch with a bunch of hosts connected. Without configuring VLANs, the switch has one MAC address table, and all connected hosts are in the same LAN, the same broadcast domain. So if one host sends a broadcast message, which hosts will receive it? All of them. The switch floods the frame out of all ports except the one that received the message. So by default we have one LAN, which is the default VLAN 1, and all hosts are in the same broadcast domain. Now I've divided the switch's ports into three VLANs. VLANs 10, 11, and 12. Each VLAN has its own MAC address table. Actually, if you use Show MAC Address Table in the CLI, you'll see all of the VLANs in one table. But internally, the switch actually has a separate table for each VLAN. So what happens now if this same host sends a broadcast frame? As you probably know by now, it is flooded only out of ports in the same VLAN as the port that received the frame. VLAN 10 in this case. And the same applies to VLANs 11 and 12. Broadcast frames in those VLANs will only be flooded out of ports in the same VLAN. By configuring VLANs, we've logically divided this single switch into multiple switches. Frames received on a port will only be forwarded or flooded out of ports in the same VLAN. Now let's compare that to VRF. Whereas VLANs are a layer 2 concept, VRF is a layer 3 concept. So we can use VRFs to divide a single layer 3 device, such as a router or multi-layer switch, into multiple logical routers. The gray box here represents a router, R1. Connected to it, we have routers 2, 3, 4, and 5. By default, R1's routing table will look like this, with an entry for each of the connected networks, plus the local routes I'm not showing here. This default routing table is called the global routing table. Since this routing table has routes to all of R1's connected networks, packets can be forwarded between all of these interfaces. For example, let's say R2 sends a packet to R5 at 5.5.5.5. It arrives on R1G1, so R1 performs a lookup in the global routing table and finds this matching route via G4. And then R1 forwards the packet to R5 via that interface. So without configuring VRFs, all of these interfaces are associated with the global routing instance, and forwarding lookups are done using the global routing table. Let's see how VRFs change that. Now I've configured two VRFs on R1. Interfaces G1 and G2 are in VRF-2.3, and interfaces G3 and G4 are in VRF-4.5. VRF-2.3 has its own routing table with the 2.2.2.0 and 3.3.3.0 networks. And VRF-4.5 also has its own, with the 4.4.4.0 and 5.5.5.0 networks. This time, what happens if R2 tries sending a packet to 5.5.5.5? Well, the packet arrives on R1's G1 interface, which is in VRF-2.3. So it performs a lookup in the VRF-2.3 routing table and finds no route matching the packet's destination. And what does a router do when there is no matching route? It drops the packet. Although R2 and R5 are connected to the same physical router, R1, they're connected to interfaces in separate VRFs, separate routing instances, so they aren't able to communicate. Let's review what VRF is and what it does. VRF splits one router into multiple routing instances, each with its own routing table. VRF refers to the concept itself, but we usually call each of these instances a VRF also. VRF is typically used with MPLS Layer 3 VPNs to keep customer traffic segmented, but we can also use VRF without MPLS, and in that case it's called VRF-lite, the topic of this video. The goal is traffic segmentation, keeping certain traffic separate from other traffic. One example is in a multi-tenant setup, where multiple organizations are using the same physical infrastructure. Here's an example. SPR1, a service provider router, connects to two different customer networks. Customer 1's C1R1 and C1R2 on the left, and Customer 2's C2R1 and C2R2 on the right. To keep traffic from these two customers separate, the service provider could assign these interfaces to VRF1 and these interfaces to VRF2. This ensures that traffic can travel between routers belonging to the same customer without getting mixed up with traffic from other customers. And the connection to SPR2 might remain in the default global routing instance, or it might use a separate VRF. So that's one use case for VRFs. But it could also be used to segment traffic from multiple departments within the same organization, if that's a requirement. It's also common to have a management VRF to keep network management traffic and user traffic separate. VRF works by associating each interface with a particular VRF. So when a packet is received on the interface, the forwarding lookup is done using that VRF's routing table. Okay, next, let's take a look at how to configure VRF-lite on Cisco IOS XE routers. Here's that network again with IP addresses added. SPR1 connects to customer 1 with the 192.168.1.0/30 and 2.0/30 subnets. And it connects to customer 2 with the 192.168.1.0/30 and 3.0/30 subnets. And each customer site has an internal LAN, 10.1.1.0/24 for C1R1, 10.1.2.0/24 for C1R2, etc. And there's a connection between SPR1 and SPR2 that we'll leave in the global routing instance. First, let me demonstrate a problem if we tried to configure this network without VRFs. I configured SPR1G1's IP address, 192.168.1.1/30. And then the same on G3, 192.168.1.1/30. But I get an error message. 192.168.1.0 overlaps with Gigabit Ethernet 1. A router can't have two interfaces in the same routing instance that have overlapping subnets. In this case, SPR1G1 and G3 have the exact same subnet. In fact, they have the exact same IP address. That's not allowed, so G3's IP address command was rejected. But it doesn't matter if the exact interface IP addresses match or not. No overlap between the subnets at all is allowed. But with VRF, this isn't a problem. Interfaces in different routing instances, in other words different VRFs, can use overlapping subnets, or even identical addresses. So in the next slide, let's configure those VRFs. It involves three main steps. First, create the VRFs. Second, assign interfaces to each VRF. And then configure routing, whether static or dynamic. Let's start with step 1. On SPR1, let's create those two VRFs, VRF1 for customer 1 and VRF2 for customer 2. There are two ways to do this, and I'll show you both. First, I created VRF1 with the command ipvrf vrf1. That's the only command that's needed, so I just exited out of VRF config mode after. This is an older method of creating VRFs, and it only supports IPv4. That's fine in this case because this network only uses IPv4, but on modern devices, you should use a newer set of commands. To create VRF2, I used the command vrf-definition vrf2, and then address family IPv4 to specify that this VRF will use IPv4. I then used end to return to privileged exec mode. So this is the newer method of creating VRFs. It supports both IPv4 and IPv6, and you should probably use this on modern devices instead of the older command. In fact, if you want to use IPv6 in your VRFs, you'll have to use these newer commands. Okay, we've created the VRFs. Now let's assign each interface to the appropriate VRF. Depending on how you created the VRF, either with IPVRF or VRF definition, you have to use a different command to assign interfaces to the VRF. On G1 and 2, I used IPVRF forwarding, VRF1, to assign them to VRF1. If you created the VRF with IPVRF, the old method, assign interfaces with IPVRF forwarding, like I did here. Notice this message that appears. Interface Gigabit Ethernet 1, IPv4 disabled, and addresses removed due to enabling VRF-1. Any IP addresses on an interface will be removed after assigning the interface to a VRF. I configured 192.168.1.1/30 on G1 before, but this means I'll have to reconfigure it. So I've assigned G1 and G2 to VRF1. For G3 and G4, I used a different command, VRF forwarding, instead of IP VRF forwarding. If you created the VRF with VRF definition, the newer method, assign interfaces with VRF forwarding. If you use the wrong command to assign an interface, nothing bad will happen, but the command will be rejected. Okay, now I used show VRF again, and you can see the interfaces now appear in the table. We've assigned the interfaces, but we still have to configure IP addresses. You can use the same old IP address command to do so. There's no VRF-specific commands here. Note that I reconfigured G1's IP address, because it was removed when I assigned G1 to VRF1. And here are the IPs for G3 and G4. Notice that there is no error message when configuring G3's IP this time. Because G1 and G3 are in different VRFs, it doesn't matter if their subnets overlap, or even if they have the exact same IP. They are part of two different routing instances. Finally, I configured an IP on G5, connected to SPR2. This connection uses the global routing instance, so I didn't assign it to a VRF. I won't actually use this connection in this video, but I wanted to show that you can have both interfaces that are assigned to VRFs and interfaces that use the default global routing instance. So here are SPR1's IP addresses. Show IP interface brief doesn't give any information about VRFs, although if you notice that G1 and G3 have the same IP, that's a hint that we're using VRFs. Now that we've finished assigning the interfaces to VRFs and configuring their IPs, we can move on to the final step, configuring routing. Before doing any configuration, let's see the routes SPR1 automatically installs in its routing table. I used show IP route, and I see the connected and local routes for its G5 interface, and nothing else. Why is that? It's because, as I said earlier, each routing instance, whether that's a VRF or the global routing instance, maintains a separate routing table. You can use show IP route, as I did here, to view the global routing table. If you want to view a specific VRF's routing table, you need to add the VRF to the command, show IP route VRF, followed by the VRF's name. So here is VRF1's routing table, including the connected and local routes for G1 and G2. And here is VRF2's routing table, with routes for G3 and G4. With this, we should have some basic connectivity. Let's test it out. I'll test by pinging 192.168.1.2 in different routing instances. First, I simply used ping 192.168.1.2. SPR1 has two connected neighbors with this IP, C1R1 and C2R1, but the ping fails. That's because the ping command uses the global routing table by default. The global routing table has a connected route for 172.16.1.0, but no routes for 192.168.1.0, so SPR1 drops the pings. Instead, I should specify a VRF with ping VRF, followed by the VRF name and the IP address. Here I did ping VRF VRF1, 192.168.1.2, and the ping worked. That's because VRF1's routing table has a connected entry for 192.168.1.0/30 via G1. So the pings went to C1R1, which is connected to G1. I then did the same for VRF2, and it worked again. VRF2's routing table has a connected entry via G3, so this time the pings went to C2R1. So we've confirmed basic connectivity here. Now let's configure routing to enable C1R1 and C1R2's internal LANs to communicate with each other, and same for C2R1 and C2R2. To enable C1R1 and C1R2's LANs to communicate, let's configure static routes on SPR1. Of course, C1R1 and R2 need routes to each other's LANs as well, but I won't show those routes here. They're just regular static routes. Let's focus on SPR1, which is using VRF. Standard static routes, configured with the usual command, enter the global routing table, so that won't work in this case on SPR1. Like when we pinged from SPR1, we have to specify the VRF when configuring the static routes. The command is IP route VRF, followed by the VRF name, and then the route's destination address, mask, and next hop. I'm using recursive routes as an example, but of course you can configure directly connected and fully specified static routes as well. So here's the command for the route to C1R1's LAN. IP route VRF, VRF1, 10.1.1.0, the /24 mask, and then 192.168.1.2. And the command for C1R2's LAN. Same command, but the destination network address is 10.1.2.0, and the next hop is 192.168.2.2. Here are those routes in the routing table. So configuring static routes with VRF-lite is pretty simple. Just remember to specify the correct VRF in the command. To test, on C1R1 I did ping 10.1.2.1, source 10.1.1.1. So a ping from C1R1's LAN interface to C1R2's LAN interface. And it worked. Note that I didn't have to specify any VRF in this ping on C1R1. That's because the VRF configurations are local to SPR1 only. The other routers, including the customer routers and SPR2, are unaware of SPR1's VRF config. So C1R1 doesn't need to specify the VRF in its ping. It only uses a single routing instance, the global routing instance. Now let's configure routing for VRF2. This time, instead of using static routing, let's use OSPF. I've already enabled OSPF on C2R1 and R2, so let's do it on SPR1. It's very simple. OSPF can be configured on SPR1 simply by enabling it on the appropriate interfaces, G3 and G4, its VRF2 interfaces. Here it is, no extra steps needed. I just configured IP OSPF1 area 0 on G3 and G4. After forming OSPF adjacencies, the routes to customer 2's LANs appear in SPR1's VRF2 routing table. If you enable OSPF on interfaces like this before creating the OSPF process itself, the router automatically creates the process. Let's check it out in the running config. This command looks a little different from usual. Because I activated OSPF on two interfaces in VRF2, it automatically added VRF-2 to the end of the router OSPF1 command. So on this router, OSPF process 1 is now bound to VRF2. Interfaces in other VRFs, or the global routing instance, can't be part of this process. They would have to use a different process ID, like router OSPF2 or whatever. So now we should have connectivity between C2R1 and R2's LANs. Let's try with a ping. On C2R1, I did ping 10.2.2.1, source 10.2.1.1, a ping from C2R1's LAN to C2R2's LAN. And the ping worked. We now have connectivity between customer 2's sites. So our VRF-lite configuration is done. Here's a review of those 3 steps we did. First, you have to create the VRFs. I showed 2 ways to do it. First, the old method, which only supports IPv4, uses the command ipvrf. The newer method, which supports both IPv4 and IPv6, uses VRF definition, and then you need to specify address family IPv4 or IPv6. You can use both if you want, if the VRF is going to use both v4 and v6. Then the second step is to assign interfaces to each VRF. If you created the VRF with the old method, use the command IPVRF forwarding on the interface. And if you created it with the new method, use VRF forwarding. The final step is to configure routing within each VRF. In this video, I showed static routing and OSPF. To configure static routes, just remember to add the VRF option to the command, so the route is added to the correct VRFs routing table. And you can activate OSPF on interfaces in a VRF with the exact same command as usual. Just note that the OSPF process is bound to the VRF. Router OSPF1, VRF, VRF2 in the example we configured. So that's how to do a basic VRF-lite configuration. Before we finish the video, let me add a little bonus at the end here. Leaking routes between VRFs using static routes. Route leaking can be configured to enable communication between VRFs. This probably isn't something you need to know for the ENCOR exam, so this will be more of a demonstration rather than a full lesson on route leaking. But let's cover a basic example. Let's say that customer 1 and customer 2 want to enable communication between these two subnets, 10.1.1.0/24 connected to C1R1 and 10.2.2.0/24 connected to C2R2. Before configuring any route leaking on SPR1, we need to make sure that C1R1 and C2R2 have routes to each other's LANs. On C1R1, I configured a route to C2R2's LAN, and on C2R2, I configured a route to C1R1's LAN. You could just use default routes, but I configured specific routes in this example. And now let's move on to SPR1. In VRF1, we need a route to C2R2's LAN, and in VRF2, we need a route to C1R1's LAN. First, I configured IP route VRF VRF1, and then C2R2's LAN, 10.2.2.0/24, with C2R2 as the next hop, and finally the global keyword. Then in VRF2, I configured a route to 10.1.1.0/24, C1R1's LAN, with C1R1 as the next hop, and the global keyword again. So what does this global keyword mean? It tells the router to resolve the next hop using the global routing table. Using static routes, you can't leak routes directly between VRFs. Instead, you have to go through the global routing table like this. So to send packets from VRF1 to 10.2.2.0/24, C2R2's LAN, SPR1 will forward the packets to next hop 192.168.3.2, and it will look in the global routing table to find that next hop. Similarly, to send packets from VRF2 to 10.1.1.0/24, C1R1's LAN, SPR1 will forward the packets to next hop 192.168.1.2, and it will look in the global routing table for that next hop. But we have a problem. Here is SPR1's global routing table. It doesn't have entries for those next hops we configured, because its G1 and G4 interfaces are in VRFs, not the global routing instance. So at this point, it won't be able to forward packets between VRFs. It can't find the next hops in the global routing table. To fix that, let's tell the global routing table where those next hops are located. I configured a directly connected static route to 192.168.3.2/32, C2R2's address, telling SPR1 that it's connected to G4. And then a similar route to 192.168.1.2/32, C1R1's address, connected to SPRG1. So you should configure a route in the global routing table for each next hop. And now, our route leaking configuration is complete. Before testing, let's do some verification on SPR1. Let's look at SPR1's routing tables to see those 4 routes we configured. Here is the VRF1 route to 10.2.2.0/24. When looking at the routing table, there's no indication that the next hop must be resolved using the global routing table instead of VRF1's routing table. And here is the VRF2 route to 10.1.1.0/24. Same thing. It doesn't say that the next hop 192.168.1.2 should be found in the global routing table, but there is a way to see that information. If you add a specific network address to the end of the show IP route command, you can see more detailed information about the route. Here is the info. Notice that it says default beside the next hop. This means the next hop is resolved using the default, in other words the global, routing table. And the VRF2 route to 10.1.1.0 says the same. Now let's check that those next hops actually exist in the global routing table. Here they are. These are the directly connected static routes we configured. 192.168.1.2 connected to G1, and 3.2 connected to G4. All that's left is to check that we can ping between these networks now. On C1R1, I did ping 10.2.2.1, source 10.1.1.1, and the ping worked. And for good measure, I tried on C2R2 as well. So that's a basic route leaking configuration. Normally, VRFs are isolated. Packets received on an interface in VRF1 can't be forwarded out of an interface in VRF2. But route leaking allows you to bend the rules a bit and enable communication between VRFs like this, offering some flexibility. Here's a summary of the key points from previous slides. I won't read these points out again, but I recommend taking notes. Now let's do a couple of quiz questions to test your understanding of VRF-lite. Here's quiz question 1. Which of the following statements about VRF-lite are true? Select 2. Pause the video now to think about the answers. Okay, the correct answers are A and C. A is correct because that's the whole purpose of VRF, splitting the router into multiple logical routers, each with its own routing table. Interfaces belonging to one VRF will only appear in that VRF's routing table. And C is correct because even if there are IP overlaps, there is no conflict if the overlapping IPs are in separate VRFs. That's another powerful aspect of using VRFs. B is incorrect because the global routing table is part of a separate routing instance from the VRFs. Its routes can't be accessed from VRFs, unless you configure leaking, as we saw at the end of this lesson. And that leads to why D is wrong. It uses the word never. But if you configure route leaking, it is possible for packets received in one VRF to be forwarded out of an interface in another VRF. So that's an exception. Now let's go to quiz question 2. You must configure VRFs that support IPv4 and IPv6 in a dual stack network. Which of the following commands will you use? Select 4. Pause the video now to think about your answers. Okay, the correct answers are B, C, D, and E. To make a multi-protocol VRF that supports both IPv4 and IPv6, you should use the VRF definition command, followed by address family IPv4 and address family IPv6. Finally, use VRF forwarding to assign interfaces to that VRF. Here's an example configuration: creating a VRF, enabling IPv4 and IPv6, and assigning an interface to the VRF. The other commands in options A and F, IPVRF and IPVRF forwarding, don't support multi-protocol VRFs, only IPv4. Okay, that's all for the quiz. And that's all for this video on VRF-lite. This is something you learned in the CCNA, but hopefully you picked up a few extra details you didn't know before. Thanks for watching, and I'll see you in the next video. Before we wrap up, I want to say a quick thank you to the channel members whose names you see on screen. Your monthly support helps me keep making these videos and keep this content free for everyone on YouTube. I really appreciate it. Thank you for your support. If the video was helpful and you want to support me, click the join button under the video. And please subscribe and like the video. It really helps me grow the channel and keep making these videos for you all. Thanks again.